Hello, welcome to the session on frequency modulation. So, in this session, I am going to talk about the frequency modulation. It is also called as the angle modulation. It is one of the form of angle modulation, and I am going to derive the equation for the narrowband FM signal. So, using this narrowband FM signal equation, I am going to calculate the corresponding spectrum of the signal. So, as far as the communication is concerned, the spectrum is one of the important aspect. So, once you draw the spectrum of the signal, then you will be able to find the bandwidth of the signal. So, first I am going to talk about what is FM, frequency modulation. So, generally here So, in the case of frequency modulation, so this is a form of analog modulation schemes. So, analog modulation schemes, the carrier is going to be a analog signal. So, carrier will be a sinusoidal wave or any form of wave that is a continuous signal. And in frequency modulation, suppose when you take this is the given message signal. This is the message signal which I want to transmit. Then I am going to select a carrier signal. I am going to select a high frequency carrier signal like this. So, this is a high frequency carrier signal. High frequency carrier signal. Then, depending upon the amplitude of signal, then its frequency will change. So, here you can take this is. So, here the amplitude is high, therefore, the deviation may be less. So, there will be some, this is a constant intervals. So, here you can see the zero crossings are equal. The zero crossings are equal. So, these are all the equal zero crossings. Whereas, once the signal becomes frequency modulated, then the frequency intervals will be different. So, here you can take this is the given signal, then the corresponding FM signal will be so here the amplitude is high, therefore the deviation will be, when the amplitude gradually increases, the deviation increases. Then it gradually decreases. Either it goes. So, here when the amplitude is high, the frequency zero crossings will be wider, and here it is narrow. So, such a signal is called as a frequency modulated signal, and here the information is contained in the frequency, right? That is one of the important thing we have to note down. The frequent information is contained here, contained in the zero crossings, whereas the amplitude of the FM signal remains the same. There will be no big differences in the amplitude. Suppose when you switch off this say this message signal, then at the output I will be getting the same carrier signal. So, this particular frequency, when the input is 0, then this frequency is FC. The input is 0, this frequency is FT. Suppose when I apply the input, then the corresponding this frequency corresponding frequency becomes the instantaneous frequency is Fc plus Kf into m of t, where Kf is the frequency sensitivity and m of t is the message signal. Therefore, the instantaneous frequency of the signal is F of t equal to, I will write in a better way, Fi of t Fc plus m of t, where Fc is the carrier frequency and Kf is the frequency sensitivity and m of t is the message signal. So this you multiply and you add up with this carrier, that will give you the instantaneous frequency of the FM signal. So in this session I am going to derive the equation for FM signal. Then we are going to classify the message signal depending upon the modulation index, and then I will derive the equation for one particular form of FM called narrowband FM signal. So now you consider a modulating signal. So modulating signal is, say, m of t. M of t is the modulating signal. M of t is the modulating message signal or modulating signal. Modulating signal as am cos 2 pi fm into t. 2 pi fm into t. Right? This is a message signal, and AM is the peak amplitude of the message signal, and FM is the modulating frequency. So now this M of t consists of only one frequency, so it is called as, therefore it is called as the single tone modulation. Suppose when the signal consists of multiple frequencies, it is called as the multi-tone modulation. So I am going to restrict only to the single tone modulation. Then the instantaneous frequency, the instantaneous frequency. So I have given in the previous slide, F I of t is equal to Fc plus Kf into m of t. Fc plus Kf into m of t. So Kf is the frequency sensitivity and m of t is the message signal and Fc is the frequency. So here the Kf is the frequency sensitivity. It is given by hertz per volt. Hertz per volt, and this will be in terms of volt. So volt and volt will get cancelled, and the final answer will be in terms of hertz. So Kf is expressed in terms of hertz per volt, and m of t is in terms of volts. Then I can substitute this m of t here. So this becomes Fc plus Kf into am into cos 2 pi fm into t. Cos 2 pi fm into t. I am substituting m of t from this equation. Then I can write this as Fc plus, this is del f into cos 2 pi fm into t, and del f is called as the frequency deviation. Del f is called as frequency deviation. So it is Fc plus del f into cos 2 pi fm into t. Then it is given as del f equal to Kf into am. Kf into am. So this is the frequency deviation, and it represents the maximum departure of the instantaneous frequency of the FM signal from the carrier frequency. How much it is going to vary. Suppose when the input amplitude is say 5 volts, what is the departure? So what is the maximum frequency it can go? So this is called as the frequency deviation. Then the angle of the FM signal, the angle is given by, can take theta I of t. The angle of the FM signal is given by theta I of t is equal to, theta I of t is equal to 2 pi integral 0 to t f I of t into dt. So we can f I of t into dt. So fi of t already I derived that as 2 pi integral 0 to t, and theta fi of t is given by fc plus del f into cos 2 pi fm into t into dt. Then I can write this as 2 pi integral 0 to t fc into dt. I am splitting this into two terms, plus 2 pi integral 0 to t del f into cos 2 pi fm into t into dt. So here fc is a constant, fc is constant, so I can take fc outside, so that I have 2 pi fc into integral 0 to t dt, plus, so here also del f is constant, so I can take outside, so 2 pi del f integral 0 to t cos 2 pi fm into t dt. Then integral of dt is t, so that I have 2 pi fc, this is t 0 to t, plus 2 pi del f, and the integral of cos theta, the integral of cos theta will be sin 2 pi cos 2 pi fm into t will be sin 2 pi fm into t by 2 pi fm. So this is sin 2 pi fm into t by 2 pi fm. Then this 2 pi and 2 pi will get cancelled, so that then I can take this as I can take this 2 pi fm outside, or I can write like this, 2 pi fm I can take outside, two pi will get cancelled, so that sin 2 pi fm into t 0 to t. Then I can write this as 2 pi fc, and the upper limit is t, lower limit is 0, therefore t minus 0. So this is 2 pi fc into t plus del f by fm, del f by fm into sin 2 pi fm into t. So this ratio, here you can see del f by fm. So this ratio is one of the important ratio, and we are going to call this as the modulation index. So modulation index beta is given by, so beta is equal to 2 pi by, sorry, beta is equal to del f by fm, del f by fm, beta equal to del f by fm, and this is called as the modulation index, modulation index. And here, depending upon the values of beta, you can take I will rewrite this equation. So this angle theta I of t is equal to 2 pi fc into t plus beta into sin 2 pi fm into t, sin 2 pi fm into t. So beta equal to del f by fm, beta equal to del f by fm, and then the equation of the fm signal, then the fm signal is given by s of t is equal to, then it is referred as AC cos theta I of t, then theta I of t can be replaced by this particular term 2 pi fc into t plus beta sin 2 pi fm into t. So S of t equal to AC cos theta I of t. So that is the equation for FM signal. Then theta I of t is replaced by 2 pi fc into t plus beta sin 2 pi fm into t. Now depending upon the values of beta, you can take you can classify fm into two things. When beta is small, this is called as narrowband FM signal. Narrowband FM. When beta is large, this is called as wideband FM. It's called as wideband FM signal. So now I am going to derive the equation for the narrowband FM signal. Then I am going to calculate what is the bandwidth requirement for this narrowband FM signal. Again, you can take I will write the equation here. Narrowband FM signal. Narrowband FM signal. So here the narrowband FM signal, I am going to take the single tone message signal M of t is equal to AM cos 2 pi FM into t. So the message signal is single tone as it consists of only one frequency. Then for the narrowband FM signal, the S of t, narrowband FM signal is given by AC cos 2 pi fc into t plus beta sin 2 pi fm into t. So this is the equation for FM signal, right? Then I can write this as, I am going to expand this term. So this is the form of cos A plus B. So cos A plus B can be written as cos A plus B can be written as cos A cos B minus sin A sin B. So A is 2 pi Fc into T and B is sin theta sin 2 pi Fm into T. Therefore, I can expand this as AC cos A cos B. So it is cos 2 pi Fc into T into cos beta sin 2 pi Fm into T minus AC sin 2 pi Fc into T into sin beta sin 2 pi Fm into T. So, I have taken the message signal as a single tone message signal. Then I have defined the equation for the FM signal as S of t is equal to AC cos 2 pi FCT plus beta sin 2 pi FM into T. So, this is the form of cos A plus B. So, cos A plus B can be written as cos A cos B minus sin A sin B minus sin A sin B. So, this can be written as AC here you can see when beta is small, what happens to these two terms? You have to see that this is the term that contains beta. So, when beta is small, or you can take when theta is small, when theta is small, when theta small, what happens to cos theta and sin theta? When theta is small, sin theta is approximately equals to theta, and when theta is small, cos theta is approximately equals to 1. So, this is from mathematics. Trigonometry, we know when theta is small, cos theta becomes 1, and when theta is small, sin theta becomes theta. Therefore, now I can write this equation as AC cos 2 pi Fc into T and cos beta, this is cos beta sin 2 pi Fm into T. So, when this beta is small, cos theta becomes 1. So, this term becomes 1. So, it is replaced in as 1 minus AC sin 2 pi Fc into T into sin beta sin 2 pi Fm into T. When beta is small, then this becomes theta. When theta is small, sin theta becomes theta. Therefore, I can write this as beta sin 2 pi Fm into T. Right? So, now we can take this is, I can write this as AC cos 2 pi Fc into T minus beta AC into sin 2 pi Fc into T into sin 2 pi Fm into T. Right? So, this is the equation for FM signal. Here I am expanding this. This is the form of cos A plus B. So, I am going to expand this as AC cos 2 pi FCT into cos beta sin 2 pi Fm into T minus AC sin 2 pi Fc into T into sin beta sin 2 pi Fm into T. So, I am expanding this using the trigonometric relation cos A plus B is equal to cos A cos B minus sin A sin B. So, that I am getting this equation when theta is small, then cos theta becomes 1, when theta is small, becomes theta. So using this equation, I am trying to simplify this into this form. So that I am getting AC FCT minus beta sine 2 pi Fc into T into sine 2 pi Fm into T. So now this is in the form of sine A sine B. So sine A sine B can be written as cos A plus B minus cos A minus B by 2. Sine A sine B is equal to 1 by 2 cos A cos B minus sine A sine B. Sorry, this is cos A plus B. This is cos A plus B minus cos A minus B. So now I am going to simplify this equation further. Simplify this equation further so that I am going to get S of t is equal to AC cos 2 pi Fc into t minus this is this I can write this by using this equation. So minus 1 by 2. So it is plus, so sin A sin B. So here already you have one minus sign, right? This is sin A sin B. So this is plus 1 by 2 beta AC into cos 2 pi Fc plus Fm into T minus cos 2 pi Fc minus Fm into T. Right? So by using the trigonometric relation, we are writing this as S of t is equal to AC cos 2 pi FCT plus B 1 by 2 beta AC cos 2 pi Fc plus Fm into T minus cos 2 pi Fc minus Fm into T. Right? So now we have to plot the spectrum of the signal. So when you plot the spectrum of the signal, the Fourier transform of cos 2 pi Fc into T will give you del of F minus Fc plus del of F plus Fc by 2. So that we will be able to draw the spectrum of the signal. We have the spectrum at this will be the spectrum for Fc. I have an impulse at plus Fc, then at minus Fc, then for Fc plus Fm. So Fc plus Fm, we have the frequency components at del of F minus Fc plus Fm plus Fc plus Fm by 2. So I have an impulse at this is Fc plus Fm. So minus Fc minus Fm minus Fc minus Fm. Then for Fc minus Fm, so it will be here Fc minus Fm. This is minus Fc plus Fm. So this will be the frequency spectrum of the signal. So this is S of t, and this is S of f. S of f this is plus f, and this is minus f. So you have to calculate the corresponding bandwidth of the signal. So bandwidth of the signal will be the highest frequency is fc minus fc plus fm minus fc minus fm. So that this is the bandwidth. So fc plus fm minus fc plus fm. So this fc and fc will get cancelled, so that I have 2 fm. So the bandwidth of the narrowband FM signal, FM signal is 2 into FM. So this is the bandwidth of FM signal, narrowband FM signal. So when beta is small, then it is called as narrowband FM signal. When beta is large, it is called as wideband FM signal. So this narrowband FM signal consists of the unmodulated carrier at FC, then a frequency component at FC minus FM, then a frequency component at FC plus FM, right? So this is called as FC minus FM is called as the lower side band, LSB, and this is called as the upper side band, USB, and this is the carrier. So this narrowband FM signal is very similar to the AM signal. Narrowband FM signal is very similar to AM signal, right? So when you say FM, generally it refers to wideband FM signal. Generally it refers to wideband FM signal, right? So how to generate this signal? How to generate this particular narrowband FM signal? For that, you can draw the block diagram from this particular equation. So this is AC cos 2 pi FCT is the unmodulated carrier. So directly we are taking the carrier, and this is sine. I have taken the message signal as sine 2 pi cos 2 pi FM into T, so that I am getting this particular term by integrating the cost term. So this is by this term is obtained by integrating the message signal, and this is by 90 degrees phase shifting the carrier signal. So then these two are multiplied, and finally you have to subtract from the carrier component. That will give you the narrowband FM signal. That will give you the narrowband FM signal. So the block diagram for generating the FM signal is as follows. Here I am going to start with the message signal. So this is the message signal. Then I can generate this sine 2 pi FM into T is obtained by integrating this particular message signal, integrator. Then the output is given to a product modulator. It is given to a product modulator. Then in the product modulator, I am going to multiply the integrated message signal by a 90 degrees phase shifted carrier signal. So here I am going to take the carrier signal. So I can take this is the 90 degrees phase shifter. Then you can supply this to the product modulator. So this is the carrier signal. Then the output product is multiplied. Then along with the carrier signal, we are going to add. We are going to subtract. So this is the here going to use one summer. Then at the output will be the desired of signal. So this is minus, this is plus. Right. So this is the narrowband phase modulator. This is the narrowband phase modulator. Here you are getting narrowband FM signal. Right. This is the block diagram that is used for the generation of FM signal. Right. So for FM is the form of modulation scheme in which the frequency of the high frequency carrier signal is varied in accordance to the instantaneous amplitude of the message signal. And here there are two types of FM signal depending upon the modulation index beta. Beta, we can classify FM as narrowband FM signal and a wideband FM signal. Then we have derived the equation for the narrowband FM signal, and we have seen the spectrum of this FM signal consists of narrowband FM signal consists of the unmodulated carrier, and then the lower sideband and upper sideband. So it is very similar to AM signal. So the bandwidth of this narrowband FM signal is, say, it is 2 FM. It is 2 FM. So it is very similar to AM signal. The spectrum is also same. The bandwidth requirement of narrowband FM signal is same as that of the AM signal. Right. So with this, I would like to wind up this session on the narrowband FM signal.